And yes, the Jamposium is this Jamposium is a play on words with a collection of sessions for a symposium. But as we are the weather band, let's have some fun and let's make this Jamposium really special. And it's really special because all of us who are joining today and tomorrow, we all already have something in common, and that is a passion for weather. And boy, what a time to schedule this Jamposium. The winter season, even going back into 2022, has been really wild for weather, for notable extreme weather. Yesterday here in Northern Virginia, even though we can say we haven't really had winter, it's still been memorable. Yesterday it was 80 degrees, and if you can see my little screen here, I clipped some forsythia from the backyard that really usually doesn't bloom until Easter. And so here we are in late February, and even while we enjoyed 80 degrees yesterday, we're potentially going to have a coating of snow tomorrow. And others just to our north really never got into the warm air and got some snow finally there in the Boston area. But we have speakers and we have attendees to this Jamposium from across the country. And so it has been wild from the Midwest, the Great Lakes. Buffalo region has been hit hard. The West has been hit hard with a series of atmospheric rivers. We have had really some notable wild weather over the last several months. And so what we're going to be doing here over the next 2 days is, one, celebrating that passion for weather, but we're also respecting the power of weather, the power of water, the fragility of our climate. And the topics that we have 6 jam sessions over the next 2 days. We reached out to our weather band members in the fall, and we asked them what topics would mean most to them in pulling this Jamposium together. And so here's what we have as a result. We have impactful, thought-provoking sessions with leading experts designed to inspire and have action taken where there's a difference going to be made in our communities. And that's really what we're all, yes, we have a passion for weather, but I think the driving passion is that impact to society. And so here we are. We have trends in U.S. severe weather coming up. We have a session that I'm really excited to moderate coming up afterward, and that's on Hurricane Ian. And then we end today with a very thought-provoking question of why we should all care about climate change. And then tomorrow we start up at noon Eastern time again with a winter weather webinar. Again, all of the really extreme weather events over the last couple of months, along with a top 10 U.S. weather events in 2022. And then we end our Jamposium tomorrow afternoon with a science, communications, and tornadoes. And communications is so very important in all of these topics. So I'm absolutely thrilled the way this Jamposium has come together. This is supposed to be interactive, engaging. So please do not hesitate to use our question and answer feature on this platform. And, it's really supposed to be a two-way engagement between our panelists and everyone participating here today. So with that, I want to pass it on to the AMS Public Outreach Manager, Gideon Allegado. Gideon.
Well, thank you very much, Doug. Thank you for that. Yes, so ladies and gentlemen, welcome. First of all, welcome to What is Reality? Trends in U.S. Severe Weather for the AMS Weather Band's 2023 Jamposium with Dr. Harold Brooks and moderated by Marissa Ferger. Before we begin today, though, I would like to address just a couple of the guidelines for our webinar. First of all, as Doug mentioned, something about the Q&A. If you have any questions during the webinar, please put them in the Q&A on the bottom of your screen. Questions for speakers submitted through the chat will not be considered. We will also have some specific time for questions from the audience after the presentation. However, there may be opportunities during the presentation itself where there are questions that could be addressed as the presentation is progressing. First of all, I'd like to introduce today's moderator. So Marissa, thank you so much for joining us today. Marissa Ferger has worked with the Weather Communications Group at Penn State University for 2 decades, where she produces and forecasts for the show Weather World and teaches courses in weather communications. Hailing from a small coastal town in New York, she credits Hurricane Gloria with fostering her interest in the weather. So, Marissa, the floor is yours.
All right, thank you so much, Gideon. Thank you all for having me here today. And I'm excited to have a very special speaker today who's going to talk a lot about his career and just about severe weather in the United States in general. It's Dr. Harold Brooks. He is a research meteorologist and senior scientist at the National Severe Storms Laboratory, which is located in Norman, Oklahoma. He has a background in atmospheric science. He has a master's from Columbia University and a PhD in atmospheric science from the University of Illinois. And his focus is on severe thunderstorms and their effects. And he has won numerous awards and accolades, and I am lucky enough to call him a friend. So welcome aboard, Harold.
It's good to see you again, Marissa. It's always fun to spend time with you.
We always have a good time. So Harold, since Gideon mentioned where my love of the weather came from, I'm curious, your undergraduate degree was in math and physics, and then you got into atmospheric science. Tell us a little bit about how you got to where you are today.
Sure. Okay. Well, I grew up in St. Louis, and so severe thunderstorms is a part of life, and tornadoes. If you ask my parents, they would have told you that there was the beginning of the circulation of a violent tornado in St. Louis. That the damage track began about a mile east of where they were living a month before I was born, so they sort of believe it was in utero that I began interested in tornadoes. But I wasn't sure what I was going to do after undergraduate. I knew I was going to graduate school, and I had the opportunity to go to the Goddard Institute for Space Studies for a summer research program where I actually modeled the Ice Age climate. And they asked me to come back for graduate school. And so I did, and I did some stuff with volcanic aerosol transport and lots of global modeling. And after a while, it was like I needed to do something a little different. And the opportunity to go to University of Illinois with Bob Wilhelmsen and model severe thunderstorms, tornadic storms came up. And that was sort of, always an interesting thing. And I kind of stumbled into it. And then Chuck Doswell asked me if I'd come do a postdoc at the lab when I got done with my PhD, and hang around for a year before I got a real job. And it's been quite a while since then, and I apparently have not found that real job yet. I've just stayed around.
So tell us your journey. Your job has been, first of all, I've never heard of the in utero aspect of finding your passion for the weather. So that's a first for me. But tell us, what you have done regarding severe weather. And I know you're known now as the climate guy when it comes to climatology of severe weather. Can you go through a little bit about your research that you've done through the years and where you've gotten to today?
Yeah, I think that for me, one of the real things is the question that we ask in the title. The what is reality is attempting to figure out, given the fact that we know that our databases and our records and all that aren't perfect, what can we say, and what do we really know, and what what's good about the databases, what's good about the reporting databases, what's perhaps not so good about them, and then how they relate to reality. One of the questions that we always face, I think, in the severe weather community is how much of our understanding of the atmosphere comes from is truly a deep understanding of the atmosphere, and how much of it is just, well, this is the thing we've seen in where we are. And so trying to understand really how the atmosphere works has been the basis of it. So I did a lot of work on attempting to figure out how to look at aspects of quality of the tornado database in particular, so a little bit more with the severe thunderstorm database, but then also how those storms relate to the environmental conditions in which they form, and how well we know those environmental conditions, how true our understanding is as we go from place to place on the planet and from time to time in the year.
So I know with tornado climatology, the magical year for reliable data is 1950. Forgive me if I'm wrong there. That's what a lot of people say. So why that date, and is there better data that has come since then? And what do you rely on for that?
Well, there's a long period of different things that we know. Some aspects of the database actually work fairly well back to 1875. We have a pretty good record of tornado deaths back to that time. And really that comes out of John Park Finley's work. He was the first person to actually try to forecast tornadoes back in the 1880s. And that was, if you think about it, that's kind of how far back he could go in easy to get to newspaper records, and what the U.S. Army Signal Corps, where he worked, was involved in. There's another date that is around 1920. It's sort of right at the end of World War I, and where the date is a little hard to tell. And that was some data that was collected by Ted Fujita and his group at the University of Chicago initially, and then improved upon by Tom Grzoulis from in a massive work on listing all of the F2 and greater tornadoes that could be found going back. And that really, around 1920, there are some aspects of the database that are pretty good that we can kind of rely on. But that's a small part of the data set, because F2 and greater tornadoes are roughly 10% of all tornadoes. So we've already thrown out 90% of the events. The next big thing that happens is officially in 1950 we start collecting data in almost real time, not quite. The National Weather Service, or at that time the U.S. Weather Bureau, had actually started doing monthly reports of tornadoes by state back actually into the 20s. But they start trying to do it in almost real time then in 1950, and really by about the middle of 1953, which is when what was called the Severe Storms Project began, which is the origin of the lab and the origin of the Storm Prediction Center. In the middle of 1953, we start actually really collecting things in real time, and that's not too bad. The next really big, and probably the biggest change in the database, actually takes place in about 1978. In the early 1970s, Ted Fujita had proposed the Fujita scale to do damage estimates of looking at the damage and doing that. And the Weather Service adopted it on sort of a sliding experimental scale in the mid-1970s. And it took about a 3-year period for it being done all around the country. And in 1978, there was an effort made to try to collect all of those reports back to 1950 and rate them. And what they did was they hired summer undergraduate students to do it, and because that's a cheap and quick way to do things. And when we look back at the record, what we see actually is that they probably overrated the tornadoes. They were given a default rating of F2, and they had to find evidence to go away from F2. And it turns out that if we look back now, it appears that if we look at just F1 and greater, or now EF1 and greater tornadoes, those tornadoes are relatively consistently counted going back to about 1953. We have about 500 of those a year. The next big thing that happens is actually in around 1990, when the Doppler radar network was put in. And it wasn't just putting in the Doppler radars that was important for the tornado record. It was actually, there was a document written by Bill Bunting and Brian Smith, who were experienced damage surveyors, in which they essentially, as part of the initial Doppler training, they taught people how to do damage surveys in a hopefully a relatively consistent way. And that became a big part now of the modernization of the Weather Service, was to collect those data in a more consistent way. We start to see some breaks that start to occur in the early 2000s, where some processes changed a little bit. And then in March of 2007, the EF scale was adopted, the enhanced Fujita scale. And we're still not completely sure of all of the effects of these changes. I think if we look at historically the database, the biggest change is the 1978 one in the retrospective ratings. And then other things have happened since then that have made some of the data less clear as for consistency. It may be more accurate. but it may not be it may not be consistent with some of the old data. We know, for instance, that the most reliable aspects of the record, yes or no, a tornado occurred on this date. Times aren't bad. Path length is not terrible. Path width is less reliable, and a lot of that just has to do with the fact that you have to look over all of the length of the damage path to get a good estimate of what the maximum width is. And that's a lot harder thing to ensure that we've gotten done. And then the rating of damage, it depends on something getting hit. If you put a violent tornado over an open area, there's nothing to rate it with. And so under the enhanced Fujita scale, it should be rated F unknown or F0 if it hit if it maybe brushed something. And so that's one thing. We don't really know what the tornado did necessarily unless it happens in a place where it hits a lot of objects.
So when we're talking about tornado data, obviously population has changed in many locations since the 1950s, and technology has changed. All of us now can document any type of weather whenever we want to because of our smartphones. How has that impacted the, all the data that you have?
Yeah, at least as important as the population changes, because we see population changes around the world too, and we have records around the world, is the existence of the system to put reports into. And that's as important as anything else, is that if I observe a tornado, I have to know to tell someone that it eventually has to get into the data set. And one of the things that Weather Service has done a much better job on in the last 30 years than they did before was emphasizing collecting those reports, getting everyone to know we need to know what happened. If in the old days it was, I might have seen something and I might tell my neighbors, and it would never get into it might make the local newspaper, but it wouldn't make any official system. And now there are probably few tornadoes that are observed that don't make it into the database. And every other tornadoes occurring that we don't really have any good observations. A tornado in the middle of the night in an open area, you wake up in the morning and there's some tree damage. Who knows what happened there? So I think that's a big thing we've had, but we certainly have much better awareness than we used to, and it's both at the individual level, but also at the system level.
So since a lot of the people who are watching this today are weather enthusiasts, in order to make a severe weather report, do you have to be a trained storm spotter, or how does that work?
You don't have to be a trained storm spotter to get something into the database. In general, contacting your local civil defense or law enforcement they will be communicating with the Weather Service office to get there. Now, what the Weather Service does with those reports may vary, depending on where the source came from. If you're, if I'm a trained spotter, say, and I call my local or I contact my law enforcement, I contact my local forecast office, they're going to know this person was trained. We know they should know what they're looking at, and that their report is considered more reliable than if I'm just some stranger that happened to call something in. And so I think that's one of the things is that, and it's important to think about when we think about how, as the public, we interact with Weather Service in terms of getting reports in there, is, I'm a lot more comfortable if I get a report from somebody that I sat in a room with them and trained them what they should be looking at. That's much more reliable to me. Even if the other report is just as true, it's a lot harder to know the quality of it if it came from some stranger.
So I guess that's a good plug for people who want to go do storm spotter training at their local National Weather Service office.
Spotter training it teaches you a lot about the weather. So hopefully it keeps you and your family safe, but it also means that we now have a more consistent and larger group of people who are providing information that we can use to make decisions on, and then actually know what the truth was after the event happened.
All right. So if you're interested in that, contact your local National Weather Service office, and they can tell you how you can get trained. So, a lot of people now, I'm going to bring up the topic of climate change. A lot of people want to know what, is there reliable data on, how, let's say tornadoes specifically, how they're being impacted by climate change. And I know there's a lot that has to be said with that.
Yeah, this is a really complicated problem. And part of it is when we think about the linkage from the planet warming to tornado occurring, or actually from carbon dioxide going into the atmosphere all the way to tornadoes. Um, there's a lot of chains in that link, or links in that chain, and they aren't all very well established as to what the impacts of things would be. This isn't like, one of the things that we know for sure that's really first order, very simple, is if you put more carbon dioxide in the air, ragweed puts out more pollen. That's a physical response of the plant. If we put more carbon dioxide in the atmosphere, the planet on average will warm. That we also know from pretty close from first principles. And so things that are related to heat waves are pretty easy to say. This is the link isn't, we don't take very many links to get there. Well, tornadoes, there's a lot of links in the chain, and some of them we expect to increase on average as the planet warms, and others are likely to decrease. So for instance, one of the main ingredients we look for is the amount of low-level warm moist air near the ground. Well, as the planet warms, that should increase, and that leads to more energy available for storms. So that's relatively straightforward. But one of the other ingredients we look at is the deep tropospheric wind shear. So the change of the winds with height over the, let's say, 6 to 10 kilometers. That's related, and on average, that's related to the equator to pole temperature gradient. Poles are warming more than the equator, so on average, that's likely to go down, and that's less favorable for storms and for tornadic storms. But the real problem we've got, or one of the real problems we've got among many of them, is that we don't really care about averages. We care about individual combinations on individual days and individual locations, and you can imagine lots of things changing about an average, but still leaving a tail that's really that doesn't go with where the average is, and that's a lot harder to come up with. And then we still have to worry about the fact that that's not everything that happens with tornadoes. We may need to worry about how was the storm initiated. So is it a long line of storms, or is it an isolated storm? What goes on inside the storm? How are the microphysical processes? So all the rain and the hail, what are they doing? They have an impact on what happens with whether a tornado forms or not. A tornado is, even on the kind of day that you're out there chasing and you're looking, and this is a great, all the environmental conditions are great. Not all storms make tornadoes. And so that becomes a lot harder then to figure out what we're trying to do when we look at it in the large global sense.
So you just said the word, chase. Can you tell us about, what is it like to be a storm chaser? And have you ever done it with an actual project that it's been affiliated?
Yes, I went out, I believe, 2 days with a real project.
Okay.
Most of the time when we had field projects, I was actually involved in forecasting as part of the support. But there were a couple of days back in 1995 when we were, or 94, when we were really desperate for people, and I got sent out in the field and got to drive in large hail. I don't chase anymore, and a lot of that is just because traffic is too bad, and I'm as I've become older, I'm less patient with people driving on the highway, and I don't really want to do that anymore. But I think a lot of it is, and I'm kind of old school. There wasn't a whole lot of data available when I started chasing, and you had to make your forecast and you lived with it. And so you'd go out in the field, and I always thought when I was a graduate student that there was a great deal of punishment for not forecasting well. So that was an encouragement for learning how to forecast, was because I just drove and used 2 tanks of gas to see nothing very interesting. I don't want to do that again. And so I think I never chased, in reality, I don't think I ever chased for explicitly scientific purposes. But I cannot separate what I did during my PhD work and in the early years after my PhD work when I was modeling storms. I can't separate the questions I asked of the models from what I saw when I was out. And I think I looked at storms when I was chasing differently because what I had seen in my simulations. And I think that was a really important byplay between what I learned in the field without intentionally trying to learn, and what I then learned from the models where I was intentionally trying to learn. And I think that was a really important uh, thing for me especially in my early days of trying to, ask better questions. There were things I saw in the model. I go, wow, that looks like the thing I saw on that day, and the other way around. I'd make different chase decisions because of what I'd seen in my model runs.
I think you just brought up a really good point, that most people may not know that tornado researchers don't necessarily go out and chase storms all the time. A lot of the time they're sitting, in the office you're sitting in right now, and they're staring at a computer. So can you tell us a little bit about how that goes? It's not very glamorous, is it?
It's not nearly as glamorous as it sounds. Like, I occasionally will get media come in and, well, can I see you working? And it's like, okay, I can put my hands on a keyboard and I can type and I can stare at the screen. If you think that's compelling television, I'm not sure I want to watch your show. I think a lot of it is that I still see myself as I like to play, and I like to play and ask questions and try to understand something about how the world works. And right now I'm doing a lot of stuff with that in some sense seems very esoteric. I'm building toy models of forecasting systems and trying to test all the parameters in that system. Whether they have any much bearing currently with reality or not is a separate question, but understand if we do this to the forecasts, what does that mean to how people can respond to those forecasts and how people can use the information from them. And I spend a lot of time thinking about how do we create models that help us understand how we can communicate information in rare event situations, which is what tornadoes are primarily.
Does that get frustrating working with those models, and you may come in with a preconceived notion of what's going to happen, and then you put in some numbers and it's what spits out is completely different?
Well, I think actually what usually happens is I put something in and I get back something that says it didn't work at all. And so it's back to let's go back and debug and figure out what went on. Or I put something in and it comes out and they say, well, that's not remotely close to reality. That happens a lot. Is that it's like and so that's part of what I think I've learned over the last few years is trying to figure out for the class of models I'm working on, which seem incredibly simple in lots of ways. It's certain things just that's not realistic. We're never going to be making forecasts like that. And so trying to come up with forecasts that are reasonably possible and realistic, and then learn how that what impacts those have on how we think we can communicate to people. And it's frustrating in some ways. I think the biggest frustration, there are times I learn things and it's really hard to communicate it in an effective way to get people to understand why this actually matters a lot. And we should be doing more. That this should change the way we do our larger scientific research, because we're not going to get to the place you think we're going to.
One of the questions that people ask me all the time is, we're in the 2020s, technology is so good, how come we can't forecast the weather? And when you're talking about tornadoes, that's a really small scale. It's hard enough to forecast snowfall amounts across, I live in Pennsylvania, the state of Pennsylvania. But when you're talking about who is going to get a tornado, where is the impact going to be felt? Why is that so difficult in this day and age of technology?
Well, a lot of it has to do with the fact that we still don't completely understand how tornadoes work. There are a lot of questions that we still have because we think a lot of it happens inside of the storm itself, and so we know fairly well conditions that are necessary for tornadoes. That these kinds of large scale conditions have to be occurring, but that doesn't mean we know what all the limiting factors that will say a tornado won't happen when these conditions are there. We also know that one of the real challenges, and this has been true for a very long time, is that we're pretty confident that in observationally at least, that places that are very important are essentially in the area just before the tornado forms. This is a really hazardous area to collect data in. Trying to collect data in air that's coming down that may have large hail and is about to have a tornado that's a risky place to put reliable data collecting instruments in, because you can lose them pretty easily. And so I think there's some there's some exciting stuff that's been started at Penn State that I think is actually addressing some of those questions. I mean, it's really hard to observe in the real world. It's really hard to observe storms making tornadoes. When we think about what radar does, there's a fundamental problem that the Earth isn't flat. That means we can't see right down at the ground, which is where we think the most important thing is, and that's just that's a limitation that we can't get away with. On top of the fact that we don't have a complete physical understanding of what's going on.
There are some people who still believe the world is flat, Harold.
I live near many of them.
So how hard is it? You touched on this a little bit, but to collect data, radar gives you some data, but you also need to know, you were talking earlier about, temperatures and, wind speeds and all that. How difficult is it to collect that? And do scientists share that data amongst one another? Are you able to get that data from other scientists?
Well, a lot of it we collect on a routine basis. I mean, we've done, we have a long record of doing, radio sound observations of the atmosphere. So we get temperature profiles, and we're able to build fairly good models that help us understand, and that's the basis of our forecasting. A lot of it, these are the conditions in which tornadic storms form and which non-tornadic storms form, and those data are collected routinely around the world. More detailed looks at storms. I think we're better than we used to be about sharing data. I don't think that's a real huge problem. One of the challenges we've got is that we have is that we really want to be collecting all that data about a particular storm. If you have really detailed, some single piece of data collection in a very detailed way on one storm, and then someone else has a complementary data set on another storm, that's not nearly as powerful as if we have all of those observations taken on the same storm, which has become the big thing about having sort of modern field projects, is attempting to collect a huge amount of information from a variety of platforms on a particular storm, so that we know as close to everything as we possibly can about that storm, as opposed to, we've got a lot of information in this one way about a bunch of storms, but gosh, we don't know this other thing. The radar data isn't as valuable without having some sense of what the temperature profiles and moisture in the area are. And the moisture and temperature within the storm may not be as good to know if we don't have any idea what the radar looks like with it. So
I see we're getting some questions here, Harold. So I don't know if you can answer this one. It says, are people aware of Dave Sills and his group in Canada, the Northern Tornadoes Project?
Sure. Yeah, I in fact just answered an email from Dave this morning regarding how to evaluate some of their forecasts. So Dave, I've known Dave for almost as long as I've known you, maybe as long as I've known you, Marissa. So that gives you an idea. It's a really exciting thing that in Canada they've just recently, in the last several years, started a project that's looking at tornadoes in Canada, and also doing some looking at hail in Canada, attempting to, 40 years ago there was very little information at all about tornadoes in Canada, even though you had to know that they had happened, and they'd had major deadly tornadoes in the past, and there would be little regional efforts. And now they've managed to put those together, and they're putting together a whole lot better approach to things. And they're also doing it in conjunction with one of the best wind engineering groups in the world. So they're actually able to do some things on how do we, given a tornado happens, what impacts does that have on structures? And so it's been a really exciting bit of work that they're doing. And Dave's the guy who knows more about tornadoes in Canada than anybody else, and probably he's one of the top people in the world on the subject of looking at it. But it's so nice to see them finally getting a good data set that we can now compare with the US.
That's awesome. And thank you to Peter Taylor for asking that question. And now we have one from Eric Levine. Do you use data from NASA's Globe Observer Citizen Science Project? I don't. That doesn't mean that other people don't. I sort of let stuff get it, or if I do, I don't know it. I typically use a lot of stuff that gets filtered through the Weather Service's system.
I don't work for the Weather Service, but I work for a closely related agency, and they and I sort of I know the quality control issues associated with that data set, and I know what the process they go through to say this is what actually happened. That makes me, it sort of relieves me of that effort of having to do that on my own, so that's why I tend to rely on what they've gotten out of that. But they do use a lot of stuff from from individuals, and we've got more of that going on in weather now. The MPIG precipitation system that was developed here in Norman, where you can essentially put in, I'm observing rain at my location, or snow or hail when it began. I remember years ago there was a really a few years ago there was a really wonderful example of actually of a snow rain line moving across New York City, and there were enough people putting in that you could actually watch the line move, and it was really neat to watch because we were getting 100 reports every few minutes, and that was pretty neat to see what was happening then.
I think that's neat just from a sense that, New Yorkers knew that this product was available to them.
I don't know where it had gotten to them, because that's one of the things you see a lot of people. I mean, Imping in Norman.
Oh yeah.
It's when I sit here and I go, well, if I can put my report in, but I know there's somebody who lives a block away from it, and the only question is, are they up on their phone at this time of night to be able to put in their report too, and all that kind of stuff.
Yeah, it was neat. Just personally speaking, last 2 days ago, we had the warm front come through, and we started with some rain mixing with sleet. And it's just so neat to see those real-time observations when you're looking at radar scope on your phone and getting to find out what actually is happening and what, is just 10 miles away. It's exciting stuff. I think we might have another one here.
Yeah.
All right. Let's see.
Yeah. Nolan Deeskin's, Deeskin asking about the modernization certainly had a big impact. The NWS modernization, which was the late 80s through early 90s, had a big effect on getting storm reports in. I mean, they now actually make a lot bigger effort, and so they now even back into the 80s, if they didn't have a forecast out for the area, a warning out for the area, there was little effort taken to collect the reports. And now the offices are much better about getting it. So we see the interesting thing about this is this comes back to the question of high quality data versus consistency. And so how there's a change in the reports there. Well, there might be offices nearby that had had a different effort prior to that, because there, when we think about, if you think about in Colorado, the office out of Boulder, there's a lot of meteorologists in Boulder too, and so you could get reports out of Boulder really easily. Neighboring offices didn't have that concentration of people, and so their record historically changes differently. And this is one of the I don't want to say concerns, but it's an issue, is that while reports have gotten better in general across the country as we've gone on in time, they haven't gotten better at the same rate in different places. And so we still depend, even in the modern era, we still depend upon a relatively small number of individuals to collect the reports and put them into the database. The best example that I can remember, this was back in the early days of the modernization. There was a forecaster who was very keen on collecting reports, who moved from one office to another office. And you could see a large increase in hail at his new office in the years after that, and a decrease in hail where he'd come from. And it was just because, in addition to being a forecaster, it seemed like he spent the other 16 hours of his day, he didn't sleep apparently, he spent the other 16 hours of his day collecting hail reports. And so that was you have to take that into account if you're looking in detail about the fact that we've had different personnel in different places, different emphases happening at different times. And that's that's again why, especially looking at the lower end reports, the smaller reports can be really challenging, because those are the ones that in some sense it takes a lot of effort to collect. If a violent tornado comes through a town, or there's softball size hail, somebody notices. and it gets into the system. But if it's a relatively small event, it may not make it into the system.
So that leads me up to another question regarding population density. You may get a lot of reports for a storm, say Florida, where there's a lot of people living, but then you go to, northern Kansas, and there aren't as many people to report this. How do you account for that?
Well, there are a couple of things we can do. One of them is we can put reports. One thing that we do is we sometimes grid reports, and we basically say yes or no, did something happen on this grid box, and that actually eliminates a lot of the reporting differences. It doesn't take care of everything, but it's a pretty good first step to say, and we look at over the course of a whole day rather than over a couple of hours, and that takes out quite a bit of the changes. We also tend again to look at higher end reports. If you look at the higher end reports, again, they're more likely to get reported. Everybody reports baseball hail. That makes it in. If it's 3/4 inch hail out in my yard, that's not big enough to really cause worse damage than the acorns do falling on my car. I don't report it. I may not report it. I may report it to make sure that the Weather Service knows that there's a severe storm, or maybe approaching a severe storm, but I'm not going to put as much effort in. And if I didn't personally know the people in the forecast office, I probably wouldn't. I might not put. If I was not a meteorologist, I might even make that much effort. But big stuff, I'm making sure it gets in because I want my insurance company to pay me for my new roof, and that's a part of what goes on. Is how does the damage actually affect someone in a way that they really want to get that reporting, and that also then has an urban versus rural bias as well. Because if I'm on a farm and a hail swath goes across, if it's a ranch and I'm not actually growing crops where I've lost my crops, and all I'm worried about is my livestock, it might not. It's less likely to make it in than if it goes across a car dealer's lot. That'll make a big difference.
Okay, that's very interesting. That was something I've never thought of before.
Yeah, it's a real issue. Okay, we have a question on the ramifications of comparing tornado intensities from the GETA scale and the EF scale. We're not completely sure about what all the differences are. We would like to think that things didn't change much, but there's some aspects that I think certainly did. And some things are very, very positive about it. We now have a set of things that a relatively small set of structures that we all can, in some sense, agree on, that we know what the damage is. We have a good idea of what the damage is. If this much of the structure is damaged, that tells us something specific. We got expert information about how to deal with that, and so I can tell, Marissa, we could give you the guide and of what the damage indicators are and all that, and you could go out and do an assessment that would look very much like the same one that I would do. And in the old days, that wasn't true. You might go out and, we just said, hey, tell me what the damage is like. And based on your experience, you might have a different answer than I do. That's a really positive thing. I think there's some, I think there's some things that have happened that we don't completely understand. Tornado path width became wider when the EF scale was introduced. And it's not clear why, except I think that perhaps it's because of the fact that we do have this consistent set of damage indicators now to look at. It made it easier for people to cover more of the damage path when they do, and make a bigger effort to look all along the path and collect data along the path, which if you since we report the maximum width, if you look at more of the path, you're more likely to see a wider thing than if you only look at one part of the path. I'm not sure. There's at least a hint of evidence that you're less likely to get a violent tornado in the EF scale than we were under the F scale. One of our challenges always is that anytime we see changes, particularly in the tails of the distribution, how much of it is physical and how much of it is just we're not looking at it the same way, because of it's possible that physical changes have happened to make the violent tornadoes less likely, but it's also possible that it's just that we don't report them the same way as we used to. I mean, we're approaching a decade since the last EF5 tornado, and so that's by far the longest streak we've ever had. But we also saw that we had a not long before where the EF scale came in, we had an 8-year stretch without an F5 tornado, and so how much of that is physical and how much of that is just, hey, we report things different than we used to, is a real problem. And that's why, in some sense, when we look at to try to see what the effect, to see if there have been changes occurring in the atmosphere physically, we have to try to look, we can't look at the most extreme events because they're such a small sample size anyway that it's hard to do things with.
Okay, so we have another question, and this was
Yeah.
actually something I was planning on asking towards the end. So thank you, Richard, for asking it. Is Tornado Alley moving east?
Well, and of course the real question there is, what is Tornado Alley? And Tornado Alley is not a scientifically well-defined quantity. People, I think if you look historically, people have thought of it as being a plains thing. And I wrote a paper in 2003, I think now, where we attempted to come up with a definition that matched that area. And it was clear then that it wasn't just occurrence of tornadoes, that there was something else must have been going on. And the thing that really defines the plains for tornadoes is a very, very strong annual cycle and a very, very strong diurnal cycle. If I live in Oklahoma City, the vast majority of our tornadoes occur in a 6 weeks either side of May the 2nd, and between 5 and 9 p.m. That's roughly 80% of our tornadoes occur in that window. You go to the southeastern United States, you go to say eastern Mississippi, where approximately the same number of tornadoes occur, and now you might be able to find a 6-week window or a 3-month window where maybe 40% of the tornadoes occur, not 80%. And as far as during the day, there's no time you get more than a 4-hour window that's more than 30%. And again, we have almost all of ours happen in that early evening. So that means Tornado Alley people didn't really ever think of it as being just occurrence. Now that said, what we have seen is an increase we've seen an increase in the number of tornadoes reported, and again with some gritting to try to slow down some of the changes, an increase over the Mid-South and a decrease over, say, the Texas Panhandle, western Kansas. And it's similar in location to some increases in the frequency of large values of some of the forecast parameters we use to forecast tornadoes. And so over the last 40 years, there's been perhaps a 10% increase in tornado occurrence over the Mid-South and a 10% decrease over the Texas Panhandle, western Kansas. But that really doesn't, only if you define Tornado Alley as being an occurrence thing would that say Tornado Alley has done anything at all. And there was actually a lot of tornadoes then. If you look back, I mentioned the Tom Grzoulis data set earlier. If you look at 1921 to 1935, the 15 years at the beginning of when it starts to be a pretty real consistent data set, the peak tornado occurrence was actually over Mississippi for F2 and greater tornadoes then. So, that was a long time ago. That's what you would have drawn if you were drawing just occurrence. And to me, the 10%, the way I think of that 10% change is there's whatever you define as a once a decade event. So from maybe a tornado that's within, there's a tornado that occurred within 25 miles of your location. If that's what a once in 10-year event is, that's changed that to a once in 11-year event or a once in 9-year event, which, I can't make any decisions in my life based on the difference between a 1 in 9-year and a 1 in 10-year event. Now it might matter if I was a state emergency manager, because a 10% change in the events is a big deal, because now that's 10% of my budget, if I'm responding. The other thing about it is that tornadoes in the Mid-South are societally particularly important. One of if you look at a map of population density in the US, the big difference when you go east of the Mississippi River is much higher rural population densities than you see in the plains. Rural population densities, say in Alabama, are 10 people per square kilometer everywhere outside of the towns. You come out to western Oklahoma, and that number's less than 1/10 of a person per square kilometer. And so a tornado in the southeast, the mid south and the southeast, is going to hit something, even in rural areas, even without getting into a town. There also is a lot higher fraction of poverty and a lot higher fraction of mobile home residents there. And so they tend to be more dangerous. And since they don't have that really strong annual and diurnal cycle, they are more likely to occur at quote unexpected times. And so there's a lot of issues that go on with why we care so much about tornadoes in that part of the country in terms of societal impacts. So 10% change in that can have a big impact.
That could be a whole other hour-long discussion about nighttime tornadoes and proper shelters.
Yes,
and all
yes,
that.
yeah. You may actually have a little bit of that tomorrow.
Yeah. So we have about 10 minutes left. We have a couple questions here. We have a question from Halifax, Nova Scotia, one of my favorite cities to ever have visited.
I'm with you on that one. My wife and I did our honeymoon in Nova Scotia. So yeah.
So with weather events becoming more intense, is there any movement toward expanding the current EF scale beyond EF5?
No. F5 is as big as it gets. We haven't seen any really evidence that there's any change in tornado intensity. That we just don't see that at all. But the scale is the way it's defined. No, it's not going to go. It's not going to go above that. Fujita, when he originally designed the Fujita scale, there were numbers that went up to F12, but that was just he was connecting Beaufort scale to Mach 1, but he actually says in his thing F5, and is the highest end for actual tornadoes, and F6 is doesn't even exist on his damage assessment.
All right, next question. How important are Florida tornadoes?
If I live in Florida, they're very important. I mean, Florida has a lot of tornadoes. They have a lot of relatively weak tornadoes. That if you look at the distribution of tornadoes by intensity in Florida, they look a lot like the intensity of tornadoes in the UK and in the southern peninsula of Italy, where they appear to be a lot of it is associated with non-supercell processes, and so their peak intensity is high. But Florida still gets the occasional, classic really large supercell tornado that can be very violent. 1998, I'm going to say, there was a big outbreak through the Orlando area, and so they do happen. And Florida is a relatively high population area. Hopefully, building codes associated with hurricane protection help them resist, tornadoes also, because your house doesn't particularly care what the source of the wind is. It cares, what the wind is.
Well, you led very nicely, segued into this next question. Is there any trend or changes in the number of tornadoes related to tropical cyclones?
It's very hard to tell if there is. Probably not. But well, let me rephrase that. The tropical cyclones lead to a particularly difficult problem in identifying tornadoes. And particularly if we look a long time ago when we didn't have Doppler radar to look in detail at the individual storms cells within the hurricane, in that if the house is damaged by wind, it's hard to tell what caused it. If it's a tornado on top of the hurricane, what the heck happened anyway? And so until we really got Doppler radar to be able to look at the individual storms inside the hurricane, it was hard to identify where intense little bits of rotation existed. We know there's been a lot of work done that shows, that the most prolific tornado producers are involved in storms moving out of the Gulf of Mexico north, making landfall there, and a lot of that has to do with where the right environments are relative to the hurricane center, so that the right front quadrant is the most likely location to get tornadoes, but if a storm is making landfall on the East Coast, that tends to not be in as good of an area for the thermodynamics. Whereas on the storms, the hurricanes coming on shore on the Gulf, the thermodynamics are in a great place when we put the right wind profiles together. And so hurricanes are tough to know, to have a whole lot of confidence in the quality of our databases over a long period of time. I wouldn't trust the data more than maybe 25 years.
So we have about 5 minutes left here. Harold, is there anything that you wanted to talk about during this that I didn't mention yet, or anything you want to talk about your current research? Or
I think one of the things that we have some pretty strong hints, and I think this is one of the results that I'm pretty sure is physically real, but I can't be confident that there isn't at least a little bit of reporting problems in it. If we look at F1 and greater tornadoes back historically, we average at 500 a year in the United States, and there's no trend in that overall number. But in the 1970s, we averaged about 150 days per year with at least one of them. We now have about 100 days. So there are fewer days per year in the US with at least one F1 and greater tornado. But the number of days with a lot of them, so, say 30 on a day, so what we would consider a big outbreak, that was 1 or 2 per year in the 1970s. And now we run a little over 2, on average 2 per year in the US, 2 to 3 per year. And so we're seeing concentration of tornadoes, more tornadoes on a smaller number of days, which is consistent with increased variability of weather occurrence. Same thing we see with the heaviest rain days have heavier rain now than they used to. And so it's possibly that, but it's also possible that we mentioned the shift in location a little bit. Well, it could be that that's an area which is more prone to having big days. And so, we have conflicting things going on. It's hard to say it's entirely a reporting change, because you would expect the number of days, if we were having a greater emphasis, we'd have more days, but we'd also have more tornadoes on those days. And so it's a really complicated problem to figure out. And what we know about the planet changing is it's hard to tell. Yeah. Okay. So tornadoes in the future. We have a question about that. Tornadoes are really hard to tell, and part of this has to do with the fact that thermodynamics increase, become more favorable for tornadoes, and the wind shear, the vertical wind shear, the organization probably becomes a little bit less favorable. And tornadoes really, really care about the organization. I'm pretty confident that non-tornadic storms, hail and high winds, will increase in frequency in the U.S. in the future. We also in the U.S. have a complication that we've seen, that convective inhibition has increased over the years historically, and will probably continue to do so. That's not true in other parts of the world. That has to do with the presence of the Rocky Mountains and the dry air that comes east of the Rockies. So tornadoes are really hard to tell. We're balanced on a knife edge, and how we fall on either side of that knife edge of the future is really hard to tell.
And one last quick question here about Dr. Fujita, who was a gifted data analyst, which I think can all agree on. Were you ever personally involved in any projects?
My biggest tie to TED in terms of research was when I was a graduate student. I led the ground survey with another student of the Allendale, Illinois tornado in January of 1989. We did the ground survey, and TED's people did the overflight. That was one of the last overflights that TED's group did, and I did a lot more interacting with one of his assistants, Dwayne Stiegler, but we actually put together the damage survey, and that was kind of neat. So I have one of TED's, really wonderfully drafted maps that includes my information from the Allendale Dale. That was my connection. He's just slightly ahead of me time-wise. So.
That's pretty cool, though, that you have that.
Yeah.
Well, it looks like we've run out of time, Harold. Thank you so much for your
Oh, you're
willingness
welcome,
to donate
Marissa.
this
Yeah.
time today and your expertise. It was fascinating. You've got great stories, and it was great to just see you again.
Yes, it is. I look forward to seeing you in person sometime in the not too distant future.
Hopefully, hopefully. And thank you to the AMS Weather Band for giving us this platform today to chat on.
Well, thank you very much. Thank you, Dr. Brooks and Marissa. Thank you so much. Folks, all Jamposium sessions will be available to Weatherband members at amsweatherband.org. And if you have further questions or if you want to talk about the webinar, members are welcome to discuss on the Weatherband Community Forum. So yes, thank you all for joining us today. Please join us for Hurricane Ian Reflections, Lessons Learned and Its Legacy at 1:15 p.m. Eastern Time. You can join the session using the link that we have just provided in the chat. But yes, that concludes this webinar. Thank you, everybody. Take care.